when this is 7404, it means that it is a NOT gate. So there are different numbers for different gates. So for NOT gates, it's 7404, and for other gates such as for AND gate, it's 7408, and for OR gate, it's 7432. So different gates have different number. Okay, so that's how you will recognize the ICs from other ICs. So as you can see, the ICs looks like a black box, as you can see, and here this is an IC actually. So as you can real, I mean it's insulator, and as you can see, these are called pins. So using these pins, you will make connections with this IC. Okay, so as you can see, this 7404 IC has 14 pins. In this side, there are 7 pins, as you can see, 1, 2, 3, 4, 5, 6, 7, and on the other side, there will be other 7 pins. So I mean, these are the pins, and how are they connected inside? I mean, what's inside? So what's inside this IC? A triangle and a bubble in front of it. It's a NOT gate, right? So in this IC, how many NOT gates can you see? 6, right? So in a single IC, we are getting 6 NOT gates. So if we need 6 NOT gates, we can use this IC. And if we need less than 6 NOT gates or equal to 6 NOT gates, we can use one IC. But if we need 7 NOT gates, then what should we do? We need another IC, right? So it can handle up to 6 NOT gates. Okay. So how are these NOT gates connected? I have shown you in previous classes that let me just draw something. So this is a NOT gate, and this has one input and one output. So if what was the function of a NOT gate? If you insert 0, you will get 1. If you insert 1, you will get 0, just the opposite. Okay, so the output will be the exact opposite of the input. That's what a NOT gate is. So here, as you can see, that a NOT gate has one input and one output. Okay, so for the first NOT gate, you can access the input of the NOT gate by using pin number 1. Okay, and the second pin number 2, is the output of the first NOT gate. Okay, so this is the output. Now, pin number 2 is the output of the first NOT gate. Similarly, pin number 3 is the input of the second NOT gate, and pin number 4 is the output of the second NOT gate. Okay, so that's how all the pins are connected. And there are two important pins for the ICs, which are those are the pin number 7 and pin number 14. So as you can see, the 7 and 14 is they are not connected with any NOT gates. So these are to power up the IC. I mean, to run this IC, we need to provide power supply to this IC. So using these pins, I mean, pin number 14, it's VCC. So that means you have to insert positive voltage in pin number 14, and you have to connect the ground of your circuit with pin number 7. So when we connect to the pins, it was always a case that we typically forgot to connect the power supply pins, and the IC was not working. And it's a common case when you will deal with this with many ICs. Yeah, typically you may forget to power up the IC. So at first, my advice is to, when you are using an IC in the in your circuit, at first connect the 14 and 7, then connect the inputs and outputs later. Okay, so when you will deal with a lot of ICs, then this will be the case for many of you. So please remember to power up the IC using connecting the pin 14 and 7. Okay, so for every IC, there will be a VCC pin and there will be a ground pin. So you need to connect them. And let's move to the next gate, which is we will use these gates actually. So I'm just introducing you to different gates. We will use those gates to design some applications. So this is the second IC here of which is AND gate, and the IC number, as you can see, 7408. So uh, you can just check on the IC, the second line as it is. We just need to remove the letters to understand, because maybe as you can see, the numbers are 7 4 and then some letters and then 08. So if you see like that 7408 in the numbers, as the numbers, then you can recognize this as AND gate. Okay, so uh, you should remember. So I think you remember that NOT gate. Sorry, this is an AND gate. This is a symbol of AND gate, and AND gate can have uh, two or more than two inputs. Okay, so at first let's deal with the two input AND gates. So this is a two input AND gate. So you will have one input and the other input. I mean, there will be two inputs. Basically, uh, this IC 7408 has two input. This is a two input AND gate IC. So as you can see, the symbols of AND inside the pin diagram. This is a pin diagram, and this is a picture of an IC simply. And this is actually a pin diagram, as you can see. So this is pin number one, this is pin number two, and this is pin number three. And as you can see, the how many AND gates can you see in the in this IC? Four, exactly. So if we need four AND gates, we can use this. But if we need more than four AND gates, we need another IC. Okay, so if we need two AND gates, we can use this. If we need three AND gates, you can use this. One AND gate, you can use this. So up to four. Yeah, yeah, it can handle up to four AND gates. And as you can see, the pin number one and pin number two are the two inputs of the first AND gate, and then pin number three is the output of the AND gate, of the first AND gate. So similarly, all the other three AND gates are connected inside the chip. And again, this is a pin number 14 is VCC, and pin number 7 is ground. So you need to connect this. So VCC should be connected to the high voltage. I mean, these ICs operate at 5 volts. Okay, so this 74XX series, these are called 74 series or 7XX series. So these ICs operates at 5 voltage actually. So in these cases, 5 volt means 1, and 0 volt means 0. Okay, so we need to apply 5 volt in the VCC pin as well to operate this IC. I mean, to uh, power up this IC, and always ground is connected to pin number 7 in this case in these ICs. And now let's move to another IC similar. This is OR gate. OR gate is this is a two input OR gate. Okay, as you can see, there are two inputs, but an OR gate can have more than two inputs. But this specific IC can handle two inputs. I mean, the OR gates inside this IC can handle two inputs. As you can see, the pin number one and pin number two are the two inputs of the first OR gate, and pin number three is the output of the first OR gate. Okay, so uh, and there is another IC, which is there is another IC. I mean, these are some ICs. I have not covered all the ICs, but for our design applications, or uh, for our design applications, yeah. So these ICs will work, but there are other ICs, as you know that there are other gates such as NAND gate, NOR gate, etc. Different gates. Uh, every gate has its corresponding IC, and if you search them on the internet, and you will get the P diagram and you can connect. But yeah, these are some examples of the IC that such as this is XOR gate. XOR gate IC number is 7486. You do not need to remember, just I am just teaching you how to just uh, recognize an IC. So if you get this IC, so what IC is this? You have to read from the I mean the letters and numbers over this IC. As you can see, the number is SN74A6 AC86, and I have told you that just exclude the letters, just focus on the numbers. As you can see, the number is 74 and then 86. So whenever you get 7486, it's a XOR gate. Okay. So and the XOR. Oh, I have not told you about XOR gate, right? Have I? Okay. So XOR. Let's XOR is a very interesting gate because the output of this gate is very interesting because as you can see, let's draw the truth table of this XOR gate. So I am drawing a truth table of XOR gate for two input. Uh, so this is the symbol of, let me draw it proper way as I have, as I'm mentioning the XOR gate for the first time. Uh, so this is the symbol of XOR gate. It's like, and it's basically an OR gate symbol, but you have another arc type shape here in the input of the OR, then it becomes XOR. The full form of XOR is exclusive OR. And as you can see, the symbol is quite similar to the OR gate. So this is exclusive OR, and the short form of exclusive OR is XOR or XOR. Someone, uh, uh, okay, someone says XOR, someone says XOR. So whatever. It's a two input gate. So what does it do? Let's draw a truth table for this. See, suppose this is input one. Let's write this x1 and this is x2. So this XOR has two inputs. The first one is x1 and the second one is x2. Okay. So let's draw a truth table and explain the operation of XOR. And this is the output. Okay. So let's see when the basic uh, functionality of XOR is matching actually. So there are two inputs, right? X1 and x2. The output of XOR is like when there is a match between two inputs, there is a match, then the output will be zero. Okay. When there is no match, if the two inputs do not match, then the output will be one. Let's just uh, check using the truth table. It will be clearer to you. So analyze these four combinations. Okay, so this is a combination, this is a combination, this is a combination of inputs. So as you can see, for the first combination, I mean, do these inputs match? X1, x2 matches because x1, x2 match because 0 and 0 both are 0. So they match. If they match, it's 0. The output is 0. And if they don't match, the output will be 1. Okay. So if for the second case, as you can see, for the second case, do the inputs match? No. So if they don't match, this is the output should be 1. And if for the third case, uh, is there any matching here? No. So this also does match. So we'll get 1. And the last one here, in this case, they match, right? 1 and 1. So if they match, the output should be 0. So this is actually an XOR gate. It actually try to matches. It actually try to match, and if there is a match, it generates 0. If there is no match, it will generate 1. Okay. So I think you are feeling that it should be opposite, right? I mean, the opposite should have some applications, right? If there is a match, then we should generate 1. Would it be a good case? I mean, there is another get like that. So that is called XNOR, which will be exactly the opposite of this thing. So this is an XNOR get. The output will be the exact opposite of the XOR. Okay, so this is the opposite of XOR is XNOR. Let's draw the truth table for the XNOR as well. So yeah, so here the working principle is totally, I mean, entirely opposite of XOR. So in the first case, so what is the principle of XOR? When there will be a match, then the output will be one. Okay, when there is a match, match equal to one. That's how XOR works. Match, when there is a match, the output is equal to one. So here, as you can see, for the first combination, the inputs are matched, right? So if the inputs matched, then the output will be one. Okay. And in the second case, they do not match, so output will be zero. In the third case, the inputs are not matched, the output will be zero. And in the last case, the output matches, sorry, the inputs match and the output will be 1. As you can see, the results of XOR and XNOR are totally opposite. Okay, so what could be there? This is matching, right? I mean, XNOR, in the XNOR, when there is a match, then there will be a 1, and there, if there is no match, there will be 0. So I have a question for you. So what could be the application case for this XNOR gate? I mean, when should we match or something? Is there any application coming in your mind? I mean, the matching. We need to match something and generate some results. Yeah, if matches, if the inputs match, then we will output one. Yeah, you can imagine that one means yes or approved, zero means denied or no, like this, and I mean, interpreting like this, do you envision any application of this thing? Yeah, sir. Yeah, of course. Yeah, search. Yeah, also, and it's a good application. And another can be password verification. Can it be? Because you will have a saved password. Okay, and user will give some input. It will match. If there is a match, then approve. If there is no match, deny. So this kind of application can be done using XNOR. Okay, I mean X or XNOR, they're pretty much opposite. So yeah, so matching is important in the case of digital circuits, because we always need to match something. When we need to match something, then we use this kind of logic case. Okay, and forward. So we will be designing this kind of thing. So this is what we will try to design. So what what is written here? Design a password protected light system. So it's what we can do in our scope. So we will do this in Tinkercad. In the Tinkercad, you will get those ICs to connect. This is actually like real world ICs. So what should we do? What will we do in this design problem? So we have to design a password protected light system where the password is a four-digit binary number. So to simplify the things, we are assuming that the password is a binary number. Yeah, but typically it's not a binary number, you know. But yeah, but if we know how the system works, we can do it for other numbers as well. So suppose here in this case, the password is a four-digit binary number. Binary number means the password can be zeros or ones. I mean, the password can be like this. Suppose the password is 0100. So this can be a password. So that's what I'm telling, that this is a four-digit binary number will be a password. We will set this password. Okay. So let's move back to the design statement. Okay. So this is design a password protected line system where the password is a 4-digit binary number. So if the internet password matches the correct predefined sorry, it will be 4 bit, as this is a 4-digit binary number. We correct this. Okay. So if the internet password matches the correct predefined 4-bit binary password, I mean, if the password matches, a green light will turn on, indicating successful access. If the internet password is incorrect, a red light and a buzzer will activate as an alert. So, in simple language, we have a saved password here, which will not be shared with the user. The admins will only can see this saved or set password, and then the user will have 4-digit binary number to insert as input. If this input is matched with the saved password or saved 4-digit binary number, then there will be a one output and there should be a green light turned on. And if the password doesn't match with the predefined password or pin, then there should be a red light, or we'll just turn on a red light in Tinkercad actually. So, and a buzzer will turn on. So that's what we need to design. It will be it can be done using the ICs we have already talked about. We can This can be designed using the XOR, as I have mentioned, XOR or XNOR, and we can use AND or NOT gates, etc. By using those gates, it can be designed. Actually, it can be solved. The design problem can be solved. Okay, so let's start this. How should we do this? I have a circuit diagram to show you. So this is how we design the problem. So as you can see, uh, I need to stand here because the microphone will be far away if I go there. So this is how we design this thing actually. So user input, as you can see, user input is a 4 bit. I mean 4 lines, as you can, 4 inputs. So what will it do? Suppose, let me show with an example. Suppose the 4-digit predefined, I mean the correct pin number is, let's do it randomly, 0, 1, 0. I have just chosen it randomly. So this is our safe password or correct password. Okay. So it will not be shared to the users. Okay. I mean, will not share to the users means in real time, you will not uh, show this. So, and user will insert for users, there will be switches like this where they can insert 0 or 1. Okay. So there will be 4 switches. Using these switches, users can insert zeros or ones. Okay. So yeah, user have a choice. Users will have a choice to put 0 here, 0 here, 1 here, 1 here. But I mean, he can put anything, 0 or 1 here as well, 0 or 1 here as well. So in every switch, uh, the user can put 0 or 1. Okay. So using this, we will actually match. So these are the users input. So let me just use different color to show users input. Suppose these are users input line. Okay, in these lines there will be zeros or ones. Okay, because just these are simply switches, and users can switch this to zeros or ones, anything. So these are the input lines. So what should we do? We need to do we need to match bit by bit, right? So this is his first bit. Okay, this is his first bit, and the correct first bit is here, 0. So we need to match this 0 with this input, right? So we need to match bit by bit. This is a 4-digit binary number, and the password is saved as a 4-digit binary number, and we need to match bit by bit. So first bit with the first bit, first bit saved pin, saved digit, and we have to match this with this, right? And we have to match the second one with this second one, right? And we have to match this third one with this third one, and we have to match this fourth one with this fourth one. So we have to do bit by bit matching. Okay, if all the bits are matched, then the password is correct, or pin is correct, right? And if any one of the bit is not matched, then it's like incorrect password or incorrect pin, right? So we have to match bit by bit. Okay, so we have to compare at first for the first digit. For the first digit, what should I do? Let me just erase them. Okay, so for the first bit, so this is the correct, bit, correct digit. Let me just erase this. So to match the first digit from the user input and from the correct saved password, saved digit. So what should we do? We should match them, right? These two. Okay. So the red one is from the user, and from the green one is from the saved digit. Okay. So if I can use an XNOR gate here, right? So what did an XNOR gate do? What does an XNOR gate do? It actually takes two input, and if there is a match, then it produce one, right? So that was the XNOR gate. If the inputs match, then the output is one. So let's insert an XOR gate here. Suppose, so the main gate should be X NOR, right? Because let me just go back to the truth table of XNOR. What we need, do we need XOR or we need XNOR? We actually need XNOR. Okay, because we are trying to match here. If there is a match, then we will be producing yes. Yes means one. Okay, so here, as I have told you, that you can interpret this one as a yes or approved, something like that, and 0 means not approved or denied, like that. Okay, so when we will approve, when the inputs will match, then we will approve, right? So in that case, we will need actually an XNOR gate. Okay, so as you can see, the XNOR gate will produce one, as you can see in the first and fourth case for combinations. When the inputs match, then they produce one. Okay, then it produce one. So that's what we need. When match, then we need one. Okay, or yes, or approved. So that's why we need actually XNOR gate. But unfortunately, in our Tinkercad, there is no XNOR gate, but we can easily make, there is XOR gate, okay? But we can easily make XNOR from XOR because we have inverter. If we insert an inverter at output of XOR, it will be XNOR. See, the same case can happen in the case of AND gate. We have AND, we have NAND, right? So if we have, suppose we need to make a circuit, and in our lab we have only AND gates, but we need NAND. Then what will we do? But suppose we have AND gate and NOT gate. Then so if we combine this AND and NOT, it will be NAND. Okay. Similarly, if we have XOR, and if we combine XOR and NOT, it will be XNOR. Okay, so in Tinkercad, as I have mentioned that there is no XNOR gate, but there is XOR gate. Okay, so using that XOR gate, we can make XNOR. Simply, this is very simple. Just add a sorry, just add a NOT gate here, and this whole thing will act as an XNOR gate. Okay, so this is XNOR. So what will this XNOR do? It will match the input from the user, which is marked by a red line, and it will match this red line with the green line. Green line means correct digit. So it will match the correct digit with the user input, and if this is a match, then it will generate a 1 at the output. So that's how we will match or try to judge the first bit of the input. Okay, first bit of the input. And exactly in a similar fashion, we will do uh, for the other bits. Okay, for the other three bits. Then for the as you can see, for the next bit, this is the next bit, and here is the correct one, and we will try to compare this. Okay, so we'll compare this using another XOR gate, XNOR gate, like this, and this will do the same thing. It will just compare the second digit, right? uh, Second digit, the second digit of the user input, which is red, and the second digit of the correct password. Okay, so if the second digit matches as well, this will generate a 1. Okay, then we'll do the same thing for the third case. For the third digit, we will use another XOR gate. We'll use another XOR gate, and uh, we will try to compare the third digit of the user input and the third digit of the correct input, like this. So this third XOR gate will generate 1 if the third bit matches with the third bit matches. Both the user input and the correct password digit match, then this will generate 1. Okay, if it doesn't match, it will generate 0, right? Okay, so for I will do the same copy pasting thing for the fourth bit as well. What I'm trying to do, I am trying to compare all the bits. Okay, not a single bit, not two, not three. I need to match all the 4 bits. Okay, because to for being a password to be for being correct, we need to match all the bits. Okay, so this is the fourth XOR gate. We'll compare the fourth input, and oh, I have done a little bit mistake because as you can see, I have connected. This is actually fourth input. Okay, so this is the third input. Okay, so this is the third input. Will go to the third XOR gate, and the fourth correct input will go to the fourth XOR gate. Okay, so this is the 4 XOR gates are actually simply matching bit by bit. Okay, so every bit is being matched, and the output will now be analyzed. So what will be the output of the XOR gate? If every bit entered is correct, then all the 4 outputs of the XOR gate will be 1, right? Uh, uh, do you get it? So if all the inputs are correct, if all the inputs match, every bits of the inputs are matched with the same password, same digit, then all the XOR gates will produce 1. And if one is done, then what will happen? Let's uh, show you with an example. Suppose, so these are the inputs. I'm just erasing this. So here, these are switches where you can insert 0 or 1. Okay. So this will represent the first bit matching result. This will represent the second bit matching result, and this will represent the third bit matching result, and the last line should generate the result of fourth bit matching. So suppose the saved password is 0010 and the user puts 0 here, the first bit 0, then it will produce the first XNOR gate will produce 1 because it matches with the saved input, okay, a saved password. And for the second case, it's the user puts 0, okay, then the uh, this is 0, the second input is 0, and here the second digit of the password is also 0, so this second XOR gate will also produce 1, okay, then the user puts 0 again, okay. So here in this case, as you can see, the third input is 0 but the saved password is 1, right? So there will be a mismatch. So if there is a mismatch, the XOR will produce 0. Okay. So XOR will because the third input is not correct and the third input is not matched with the saved password, the third XOR will produce 0. Okay. But suppose the last one is 0, the user inputs 0 in the fourth digit, and as you can see, the saved password is also 0. The last digit or fourth digit of the saved password is also 0, so it matches. Then the XOR will produce 1. Okay, but is the whole password correct? No, because if one bit mismatches, we don't call it a correct password, right? So when you set your password, if one capital letter and small letter mismatch, then your password is wrong, right? So here in this case as well. So if there is one wrong digit, then the password is wrong. Okay, the whole password is wrong, considered to be wrong. We will not approve this access if he mistakes one digit. Okay, so all bits should be correct, right? So when it should be correct, if the user would insert 1 here, right? If user would insert 1 here and the saved password is also 1, so this XNOR, the third XNOR will produce 1 as well. 1. So when all the XNOR outputs are 1, then the password is correct, right? When all the inputs are all the XNOR outputs are 1, all the XNOR produces output 1, then all the 4 digits are correct. Then using this, what can we do? So here this is a logic actually. So using this the 4 results, how should we design this next circuit? If all these digits match, all these passwords are digits are correct, then we have to turn on a green light, okay. So to turn on a green light, the green light needs 1, okay, high voltage, not 0. If you suppose there is a green light, suppose we need to, this is a green LED. So the LED will have typically an LED will have two terminals. The one terminal will be grounded. This is common ground of the circuit. You will have a ground in your circuit, and you need to connect this ground. And the other terminal should be your input actually. So if the input of the if the LED gets 1, high voltage, then it turns on. But if it gets 0, it will not turn on. It will not turn on, it will be off actually. So to turn this light on, we need to insert 1 here. So analyzing these 4 results, we need to turn this LED on. So how should we connect this 4 to this LED? What do you think? When should this LED turn on? When all these 4 XOR outputs are 1, right? Then it should be turned on. If there is 1 0 right here, then the LED should not turn on, right? So how can we do that? Exactly, yeah. So we have when there, I mean, there should be something in between here. So there should be, let me just clear the mess. Okay. Suppose, so there should be something here, okay, which will take all these inputs and produce one output. Okay. So it should take four inputs and produce one output. So when it should produce output one, actually when uh, all the inputs are one, then it should produce one, right? Because that's what we need actually. So for to turn this light on, we need to make all the we need to have all these four inputs to be one, right? So these things can be done using an AND gate. So what an AND gate does, it takes inputs. If all the inputs are one, then it produces one. Otherwise, it produces zero, right? Uh, this is the, I mean, this is the characteristics of AND gate. Okay, so when let me show you the truth table of AND gate, then it will be easier for you. Uh, and get truth table. Okay. Okay. So as you can see that the output is always zero. Whenever the both inputs is the both inputs are one, only then it produces one, right? So we need an AND gate to do this. Okay, let me go back. So here we need an AND gate, basically a four input AND gate, because the AND gate should take four inputs, and if all the inputs are one, then it will produce one. And this one we will transfer this one to the LED, so that when all the inputs are of this AND gate, when all the inputs are one, then it will produce one, and then that green light will be turned on. But if one of these inputs, suppose the second input is zero, okay, suppose this the user puts a wrong digit in this wrong input in the second digit, then the second XNOR gate will produce zero. Okay, so then the AND gate, as we have mentioned, that AND gate will produce one only when all the inputs are one. But here there is one zero, so the AND gate will produce zero, and the LED will not turn. Okay, so that's actually what we are going to do. So we need four input AND gate. Yes, there is an IC in the Tinkercad. Luckily, unfortunately, we have an IC in the Tinkercad with four input AND gate. If we do not have four input AND gates, then we need to use multiple two input AND gates to make this four input AND gates. But luckily, we have four input AND gates in Tinkercad. And so let's try to design this. I mean, let's try to connect this circuit in Tinkercad. Let's using the IC. Okay, so this is one thing to design on the scratch, and but connecting the IC is another thing. You need practice for that, and if everybody would open the Tinkercad in your laptop, it will be better actually. So please try to open the Tinkercad. So create a new circuit. Uh, I mean, we'll use the ICs and etc. in this Tinkercad. Okay, so have you been able to open the Tinkercad or? So, yeah, great. So let's try to insert the we need x nor, but as I have mentioned that we do not have x nor, but we do have xor. So here in the search box, as you can see here, uh, just search for xor, xor. There will be a IC showing under this, so you have to just click it uh, and bring the mouse on the screen and just place it there. Okay. So this is the IC. As you can see, the number is 7486, excluding the letters. So 7486. And if you hover the mouse on the pins, just you will see that this is input 1A, this is input 1B. 1A means the first input of the first, this is a two input XOR gate. So uh, let me show you the pin diagram so that it will be easier. XOR, right? Yeah. So this is actually the pin diagram of that IC. As you can see, the first pin is the first input of the XOR. The second pin is the second input of the XOR, and third pin is the output of the XOR. Okay. So we need four XORs, right? Here, as you can see, this is our circuit. So we need one, two, three, four XORs. And in that IC, we have four exhausts. That's why I actually chose 4 digit. Otherwise, I could choose 5, 6, etc. Because we can just design it with one IC. That's why I chose 4 digit. So there are four exhausts. We will be using all these four exhausts. Okay. So this is so one IC will be sufficient for our design, right? So only we do not need four of these because we already have four exhausts inside this one IC. Okay. So, and this kind of ICs are called dual inline package, deep dual inline, because some ICs have pins in all the four sides. Okay. So in this case, in this IC, as you can see, pins in the top side and the bottom side. I mean, there in two sides of this chip, there are pins, right? So the other sides, I mean, the left side and in the left or right side, there is no pin. So this is dual line pin. I mean, that's why it's called dual inline package. I mean, this is package IC because that's why it's dual, because the pins are in two sides of this IC. Okay, so we will need one of these ICs, and we need, as you can see in our design, we need four NOT gates as well, right? So we need NOT gate IC in the Tinkercad. So let's search for NOT as well in the search box. Just search with NOT. Nothing is coming. So you have to type inverter, not not it's inverter. You have to type inverter. Then there will be IC called hex inverter. You have to use this hex inverter. This is the IC. As you can see, the number is 74, then some letters and 04. So 7404 is for NOT gate. And how many NOT gates inside this IC are inside this IC? Let's see the pin. So for that, we need the pin diagram. That's why we need the pin diagram. Okay. So because by observing this IC, we cannot tell anything, because where is the input, where is the output? We do not know, right? By seeing this IC, we cannot tell that while the input was the output. So for that we need pin diagram. So pin diagram is available on the internet. Just search with the IC number, you will get the pin number. Okay, so just search. Okay, let's. So that's what I did for making the slides. I searched on the internet and get those pin diagrams. So let's go for the NOT gate. So this is 74AC04. This is in the slide. As you can see, there are 6 NOT gates inside this IC, but we will need 4. So I think this one IC will suffice, right? So we do not need more than one ICs, because one IC contains 6 NOT gates, but we need only 4 in our design. As you can see, let me show you the design. Here is the design, and you will need only 4 NOT gates. Okay. Oh, sorry. So we'll need 4 NOT gates, and we have already 6, more than enough NOT gates inside the one IC. So let me go back. Yeah. So this is one NOT gate. Let's start connecting before proceeding to the other part of the circuit. Okay. So as I have mentioned, that user will provide input using switches, right? Let me just remind you that, as you can see, these are switches. Using these switches, the users will insert ones or zeros. So to use a switch, we will be searching for. So let's take switches. uh, we can use a slide switch. If you search with switch, then several switches will come. Let's use slide switch because it's as I can see, this is simpler. So let's take switch. So this is a three terminal switch. I will describe the functionality of this switch later. Let's take, so this is one switch, and in our design we need four switches, right? Like this, because user will insert input using four switches, so we need to take four switches. So just take the copy and pasting also works here. Just select this component and just press Ctrl plus C from the keyboard and just paste it somewhere else, control using Ctrl plus V. Okay, so just copy three more, because we will need four switches. So at this point, let's take a breadboard, okay? Because it will be easier for us to place these things on the breadboard. So at this point, let's take a breadboard as well. Just in the search box, type breadboard, and we do not take the breadboard small, rather uh, take this breadboard. This is a standard size breadboard. So let's put it somewhere. Okay. So now let me describe how these switches work. So this, uh, okay, after you take the breadboard, yeah. So let's describe this how these switches works. So this switch has three terminals. Terminal, as you can see, if you hover over the pins, there will be the name of the pins. Terminal one, common, and terminal two. So let me describe using a whiteboard how this works. So okay, this is called slide switch. Okay, so let me describe how this switch works. So this is the switch, and this has four terminals. This is terminal number one. This is common terminal. This is terminal number two. So uh, suppose you want to control a light. So this is suppose. Let me draw this properly. So this, suppose this is an LED, and one terminal is grounded. This is ground. So to turn this LED on, so we want to control this LED using this slide switch. Okay. So how should we connect this slide switch with this LED? So there is a there is a middle pin. So the middle pin should be connected to the device that we want to control. Okay, so the middle pin should be connected to the device that I want to control. So I want to control this LED, so I need to connect this here. Okay, and then this is one terminal, and if you connect this to 5 volt, suppose this is connected to plus 5 volt, and the third terminal is connected to 0 volt. Okay, then what happens? Then there is a slider here. This slide can move left and right. Okay, this slider can move left and right. So here, if you move this slider to the left side, currently it is in the left side. I have drawn this. Let me just draw from the mid position. Yes, that way the explanation will be better. Okay, suppose the slider is here. So the LED is not connected to anything, 5 volt or 0 volt. But if you slide the switch to the left side, what will happen? If the slider will be here, and the LED would be connected to 5 volt, because the left pin is connected to 5 volt. So if you slide the switch left, the 5 volt will be activated. Okay, and if you slide the switch in the right hand side, then it will be connected to 0 volt. So that's how it can it makes the connection actually. So if you slide it left, it will be connected to the left pin. If you slide it to the right, it will be connected to the right pin. Okay, so by sliding left, we are providing actually what, logic 1, right? Because as I have mentioned that uh, the 5 volt here is logic 1. Okay, and if we slide this to the right, it will be connected to 0, that will present logic 0. So that's how user will give input. Okay, so if we will connect the first terminal to the 5 left terminal to the 5 volt and right terminal to the 0. If the user slide it to the left, we will this will produce 1. And if it is slided to the right, it will produce 0. So that's how user will give us input. So let's do that in the Tinkercad. Let's connect this. So suppose let me just put it right this way. Sorry, placing a little bit far away to keep it less messy. So this is the first switch. So we need to create some uh, voltages. I mean, to we need to provide 5 volt. So to provide voltages, we need voltage sources. So to get voltage sources, you need to just voltage. So you need to type just voltage or power, whatever. You can type voltage or you can type power. Let's type power. Okay. So power, and there is a component called power supply. Okay, this component I am referring to this component. So this is a power supply. We will use this to supply power to different things in the circuit. So we'll use this. Okay, so just I'm clicking this and just putting it here. So this will be our power provider. Okay, and this power supply has two terminals actually. This is a positive terminal, the red one, and the black one is the negative terminal. Okay, so let me connect, as I have mentioned that I will connect the left terminal of this switch to 5 volt. Okay, so as you can see, I have connected 5 volt. I mean, this power supply will generate 5 volt. Okay, we will set that. So I have connected the positive terminal of the power supply to the left sided pin of the switch, and rightmost terminal we need to connect 0 volt, right? So from where we will get the 0 volt? The negative terminal, I mean, the negative terminal of the power supply, which is the black pin of the power supply. So let me connect this. So that's how I have connected. So the slide switch, the left terminal of the slide switch will get 5 volt, which is connected to the red, and the rightmost switch will be terminal will be connected to the black terminal of the power supply, which will provide 0 volt. Okay, so this power supply, the positive one, I mean, the red one will supply 5 volt, and the black one will supply 0 volt. Okay, so our slide, the first slide switches 5 volt and 0 volt are connected. In the same way, all the switches will be connected. Okay, so for all the switches, we will connect the left panel, I mean left terminal with the positive voltage. So just what will I do? Just I will make a shortcut. Uh, so yeah, you can connect like this. So what will happen? As you can see, the left terminal of the second switch is connected to the left terminal of the first switch. I mean, all the left terminals will be connected to 5. Okay. I mean, this is the second switch is indirectly connected to 5 volt. In similar way, I will connect all the switches. And in similar way, the rightmost terminal will also be connected of all the switches. So as you can see, all the left terminals are connected to 5 volts. Okay. And all the rightmost, I mean, this terminal, I want to assign it as 0 volt. That's why I connected all the right terminals to the 0 volt. Okay. So all the switches left terminals and I mean all the left terminals and the right terminals of all the switches are connected to either 5 volt or 0 volt. Okay. So left terminals are connected to 5 volt and right terminals are connected to 0 volt. Okay. And now the switches are powered up. Now here, let's go back to the design. We have just created the switches, right? And there's the and the we have only the middle terminals left, which will be connected to the circuit, right? So as you can see, the switch where these switches will go, it will work as an input of the XNOR gate, right? So the middle terminal of the switches will the input of XOR gates. So which one is our XOR gate? Uh, so this is 7486 is our XOR gate. The input the first two terminals are the two inputs of the XOR gate, right? The first two terminals. So as I have mentioned that one terminal should be the user input, right? One terminal of the XOR will be the user input. So let's connect this user input to, so this switch is the user input actually. Okay, these switches are user inputs, and let's connect this the middle terminal of the first switch to the first input of the XOR. So this is the first input of the XOR. As you can see, let's uh, keep the spin diagram side by side. That way, you can compare them easily. So let's just take a snapshot. Okay, so as you can see that the first pin, this pin number 1, is one input of the XOR gate. Okay, and what would be the second input of the XOR gate? Here as you can see, this was our XOR gate. The first input will be the user input, which will be provided using the switch. And what will be the second input? The second input of the first XOR gate is the saved password, right? Saved digit. So now we have not yet designed any saved digits or anything in the circuit in the Tinkercad, right? So we have to make something that will actually show as an saved password. So let's mimic this in this way. So how we can take another power supply here. So these power supplies will produce zeros or ones. I mean, by 0 means 0 volt, and when it will generate 5 volt, that means it is generating 1. So we will take 4 of these power supplies as the saved password. Okay, so let's just copy and paste it and use 4 of them. Okay. So these four power supplies will save the password. I mean, save the store. I mean, store the password, the correct password. Okay. So these four power supplies will save the correct password. Okay. So let's go to the first one. So the main thing, I mean, the main terminal is the positive terminal here. So the positive terminal here will be used as the correct password input. Okay, the correct password. So let's connect this positive terminal to the second pin of the XOR. So let me just, yeah. So we have connected the inputs of the XORs, of the fast XOR. The fast input is from the switch, which will be provided by the user, and the second input will be the saved password. The saved, we are mimicking the saved password by using a power supply. The power supply will provide a certain amount of voltage in its positive terminal. Actually, we will provide 0 or 5 volt using this positive terminal. Okay. And what will we do with the negative terminal of the power supply? You can connect it to the a common ground. We will make a common ground in the breadboard. Okay. So let's connect this to a breadboard, line. And did you remember that, how the breadboard pins are connected? These pins are connected horizontally, right? And this here is a minus sign, there is a plus sign. So these two lines are connected. I mean, the first line is connected horizontally. The second line is also connected horizontally. So this pin, suppose this pin and this pin is actually equivalent. I mean, if you connect here, it will be automatically connected here. Okay. So I am creating a common ground because there will be a lot of grounds coming from the power supply. As you can see, there are four power supplies, and all those power supplies have ground terminal. So the ground terminal should be connected to the common ground of the whole circuit. So let me connect them actually. So I have connected the ground or the black terminal to the common ground. I am trying to make a common ground right here in this line of this breadboard. So and big and this is another power supply, right? So all the power supplies ground should be connected here. Okay, let's keep it like that. Okay, so now let's move to the second input, right? So as you can see, the second XOR has inputs in its four pin number 4 and pin number 5. We are not dealing with pin number 3 yet because we have just given input to the first XOR gate, but we have not uh, done anything yet with the pin number 3 because it's the output of the XOR. We will use that later, but let's connect the inputs of the exhaust first. Okay, so the second exhaust inputs are pin number 4 and pin number 5. Okay, so in a similar way, let's connect the second input here. I'm connecting the second input from the second switch and connect it to the pin number 4 because pin number 4 is the first input of the second exhaust. Let me show you again. As you can see, I have connected this pin. I have connected this pin right now. Okay, so I'm using the second XOR gate, and the first input would be the input from the switch. I mean the second switch. And what should be the second input? I mean pin number 5. This should be from the saved password. Okay, the saved password are in the power supply above. Okay, so I am using the positive terminal of the second power supply, which we are treating as the saved password, and the second digit of the saved password specifically. So I'm connecting it to the pin number 5. Okay, I mean the second input of the second XOR gate. I mean here, this one. So I'm currently connecting the XOR inputs, right? So I have connected first XOR, I have connected second XOR. Now let's move to the third XOR. In a similar fashion, the third XOR's first input would be the input from the user switch, right? So where is the third XOR? As you can see, you can mark this XOR as third XOR as well, but they marked as you can see, the numbering shows that this is the third XOR. So third XOR's first input is pin number 10. As you can see, pin number 10 is the first input of the third XOR. So by observing this pin diagram, you have to connect the ICs actually. So the first input, I have moved to the third XOR. So third XOR's first input would be the input from the switch, right? I mean the user switch. So I'm connecting the user switch to the pin number 10 of the IC. That's in this way, this pin is connected. Okay. The third XOR's first input is connected through the IC. And what will be the second input? The pin number 9 is the second input of the third XOR. So it will come from the power supply, right? Which we are we are mimicking the step password from this power supply using this power supply. So the third power supply will be connected to this pin number 9. I mean, this is the second input of the third XOR. That's why I have connected. Again, uh, um, I'm telling you that I have not connected any of the outputs of the XOR yet. I am just connecting the inputs, which are coming from the user switch and the power supplies that we are uh, marking them as uh, saved password. So now let's move to the fourth XOR. So the fourth XOR, as you can see, the fourth XOR's first pin is at pin number 13. Okay, pin number 13 is the last XOR's first input. So let's connect this with the switch, user switch. So here is one of the connections. So let me show you. So I have connected the first input of the last XOR, which would be connected from the switch of the user. Then the pin number 12 will be connected to the power supply. Okay. These power supplies are the saved inputs. Okay. So that's how I have connected the XOR. So for all the XORs, for the first input, I have connected the switches to the first input of the XORs, and the second input of the XORs will come from the power supplies. Okay, and we have to connect the power supplies negative terminal as well. As you can see, the second, third, and fourth terminals, negative terminal or ground terminal, I have not connected this. So let me connect this to this negative terminal. I mean that I have created in the breadboard. Just I'm connecting this negative terminals of the power supply to the negative, I mean ground node of the breadboard. So I have connected all the black terminals to this line of this breadboard. So I am treating this as my ground terminal or ground node. Okay. So I have connected the power supplies, the input. So we have connected up to this point. We have connected these things. Okay. So we have implemented all these things. Now we move to the next part. So we have to connect NOT gates in all the outputs of the XOR. Okay, so we have not connected the outputs of the XORs yet, but we have to connect a NOT gate with the output of the XORs. So let's go back. So as you can see that the four outputs of the XORs are at pin number 3, pin number 6, pin number 8, and pin number 11. So as you can see, the outputs are at 3, 6. We have not connected the outputs yet, right? pin number 11, pin number 8. We have only connected the inputs of the exhaust. We have not connected the outputs yet. So what should be connected to the output of the exhaust? A NOT gate, according to our design. Okay, as you can see that the at the output of the XOR gate, as you can see at the output of the XOR gate, the output of the every XOR gate actually is connected to a NOT gate input. Okay, so we have NOT gate IC here ready, 7404. So let's take the uh, at this point we will need the we'll need both the pin diagram of the XOR and NOT. We need to keep it side by side, right? It would be when we will make the circuit, if you take the electrical engineering as your major, you will deal with this. So make sure it will be easier for you if you print them out, because you have to deal with multiple ICs. So in that case, you print them all out and then keep in front of you and just compare them. Because here at this point, I will need the pin diagram of both ICs, right? Because I will connect the output of the first IC to the input of the next IC, right? So we need to know the inputs and outputs of both ICs actually. So here is the sorry. So let me divide this. Mm, What is the sleeping to here? I'm trying to just keep the pin diagram side by side. Okay. Mm. And we also need the NOT gate IC pin diagram. My God. Okay. Here we go. Okay. So, yeah. So, what did I tell you? That the output of the XOR gate should be connected as the input of the NOT gate, right? Because uh, here I have shown you in the design that, as you can see, the output of the XOR gate should be connected to the input of the NOT gate. So, let's do that. Okay. So, the first output was pin number 3, right? Pin number 3 was the output. Uh, Let me take a pencil. Uh, oh, Brazil one. Okay, so the output of the pin number 3 should be connected as the input of the first NOT gate, like this. Okay, so we need to connect like this. So pin number 3 of the XOR IC should be connected to the pin number 1 of this NOT IC, right? So let me connect that. So here, let me zoom in, and this is the pin number 3, which is the output of the first XOR. Let's make a connection and take it to the input of the NOT gate. The first pin, I mean pin number 1 of this IC is the input of the first NOT gate. So I have made this connection. As you can see, I have made this connection. I mean the output of the XOR is connected to the input of the NOT gate. Okay. Uh, have you understand it? Okay, so good. So in this way, I have to connect all the 4 XOR outputs. Okay, the second XOR output is at pin number 6, as you can see, pin number 6. So pin number 6 and pin number 6 should be connected as the input of the second NOT gate. Here, as you can see, this is the second NOT gate. Second NOT gate input is at pin number 3. Okay, so I am connected. Here is the output 2. I mean, this is the pin number 6 actually. Pin number 6 is the output of the second XOR gate. Okay, and this should be connected to the input of the second NOT gate. So input of the second NOT gate is here, pin number 3. Okay, here. So I have connected the output of the second XOR gate to the input of the second NOT gate. And I have not used the in output of the first NOT gate yet. It's output. I have not connected it yet, but I will connect them. At first, I'm connecting the inputs of the NOT gate. Okay. Now let's move to the third XOR gate. Third XOR gate's output is at pin number 8. Pin number 8. Okay. So where is pin number 8? Here is the pin number 8. It is the output of the third XOR gate. Okay, so let me connect this to the input of the third NOT gate. I'm making messy connections here, but yeah, just we do not have much time, so that's why. But in professional case, as you can see, we will just show you in the next class. Maybe we'll show you layout. Layout means you have to how the chips are made. I mean, how these ICs are connected and etc. etc. So as you can see, this in this simple circuit, there are too many interconnects, right? But what when there will be billions of transistors, how there will be like this kind of there will be billions of interconnects. How will you manage them inside? But here, as you can see, this line and this line is not connected, right? Because this is one other line, this is another line. Is there any connection here? No, I do not have any intention to connect this because this is one thing, this is another thing. Tinkercad does not do this, does not connect this. If you explicitly mention that this should be connected, this is just going over this. This is going over this, but these two are not connected, right? I mean, this wire and this wire is not connected. But when this is not connected, but when you practically you will make it, then what you need to do? These two wires should be in different levels, right? Because otherwise they will be connected because they are wires. And in this case, this is yeah. In this case, there are plastic insulator wrap around the wire. But when you design chips, there will be no space to wrap this with plastic. Because as you can see, in millimeter, there will be billions of transistors. So we do not have any scope to insert plastics or anything like that. So you will have dual connections. So if the connections are dual, then if they process each other in the same level, they will be connected, which we do not want, right? So that's why they needs to be in different levels vertically. So if one line goes like this, the other line should be above this. That's how you will not connect these two. Because I don't want to connect these two. So that's why you need to make them vertical. I mean space vertical. So but there will be millions of these kind of levels. So yeah, it's very messy to design chips because that is being done currently using computer simulations or etc. But doing this thing manually is impossible. Okay, so that's why the software Cadence comes. Okay, so Cadence can design these metal layers. If you connect them, they will create some metal layers. So that's where the ICs and transistors will be done. So that's a different thing. That's a different lecture actually. When we will talk about the layout design. That's for layout where we will practically design. I mean, how the practical design should look like. Okay? We have to design this right way, like that way. Actually, you have to put transistors, you have to put connections between the transistors and to where these connections will be at what level. You have to mention all those things in the layout. Okay. So that's it. That's actually a different lecture that will come in the next few classes maybe. So, yeah, these connections are messy, and we have to manage everything because, and a small mistake in connections will just disrupt the circuit. So let's again let's move back to where we were. So we are connecting the pin number 8, I mean third exhaust output, to the input of the third NOT gate. As you can see, let me just, where is the third NOT gate? Here, pin number 5 is the input of the third NOT gate. So let me connect the pin number 8, which is the third exhaust output, to the input of the third NOT gate, which is pin number 5 here. Okay, so I have connected pin number 8 of XOR gate, I mean the third exhaust output, to the input of the third NOT gate. Okay, now let's do the same thing for the fourth, or the last one. So fourth output of the XOR gate is at pin number 11, right? And the input, we have to connect this pin number 4, I mean the output of the fourth XOR gate, to the input of the NOT gate, fourth NOT gate. So this could be the fourth NOT gate. So this pin number 9 is the input of the fourth NOT gate. So we will connect the fourth exhaust output, which is pin number 11, to the input of the fourth NOT gate, which is pin number 9. Sorry. So let's connect this. So this is pin number 11. Yeah, the advantage of using Tinkercad is when you just hover mouse, it will tell you this is output, this is input. But in real life, it will not show input and output. You have to just match them with the pin number. You have to count the pin number, the pin number 10, pin number 11, pin number 13. So that's a hectic work actually. But in Tinkercad, yeah, if you hover, then you can just uh, know which is the output. Okay, so I'm connecting the last output to the input of the NOT gate, which is pin number 9 here. So yeah, so we have connected all the XOR outputs to the input of the NOT gates. Okay, now uh, oh, oh, let's see how much circuit did we implement already. Have we implemented? So we have right now, let me change the color. Okay, so right now we have implemented this NOT gates, right? So we have connected the exhaust output to the NOT gate, and we have the currently we have the NOT gates outputs, right? Now, as we have mentioned that we need to place an AND gate and deliver these all outputs of the NOT gate to the input of the AND gate, 4-input AND gate. Now we will need a 4-input AND gate, right? And we will connect the 4 outputs of this NOT gates to the 4 inputs of the AND gate. Okay, so let's take a AND gate. We have not taken the IC of, okay, IC of the AND gate. So just type search for AND gate. You will get, I think. So search for AND gate IC. And you need to make sure that we need to take the AND gate with 4 inputs. So there are versions of AND gate, different as you can see, these are different versions of ICs. So not all the same, because there are something you have to start. So as you can see, quad AND gate, triple 3-input AND gate. This IC will the AND gate of this IC will have 3 inputs. Okay, and usually the above one, quad AND gate. Sorry. So this quad AND means quad means have four ANDs. Yeah. So quad means there are 4 ANDs, but their inputs will be the number of inputs will be 2 actually. So 2 input, 4 ANDs there. So what do we need? We need this one. we need four input AND gate, right? So why is it written dual? Because there will be two AND gates inside this IC. Okay. Let's what is the IC number 7421? As you can see, 7421. So let's search the pin diagram of the internet. Okay. So let's search for 7421. Uh, just write 7421 pin diagram. That's how 7421 pin out or pin diagram, whatever. So this is so we have actually taken this IC in the pin gate. As you can see, this is an AND gate, and this has four inputs: one, two, four, five. Okay, these are the four inputs of the AND gate and one output of the AND gate. And there are how many AND gates are there inside this IC? Two. That's why the name was dual four input AND gate. Okay. If there was if there are four AND gates, then it would be called quad two input and etc. So that's why there are two AND gates. That's why it's called dual four input and IC. So, oh, okay. So let's go back and take this dual four input AND gate 7421 IC number 7421 and place it somewhere here. Okay. So again, we need to check the pin out and then we need to connect. So let's keep it side by side. Don't save. And where is the pin diagram? Here. Okay. Okay. So this is the four input pin diagram. Sorry, four input AND gate. So how is our connection? Okay. So how is our connection? So we have XOR gates and we had NOT gates. We have connected the NOT gates already. Keep another one right. Okay. So we have connected this already. And now we have to connect the four outputs of the NOT gates to the input of an AND gate. This is the big size AND gate which can take four inputs. Okay, and one output can generate one output. So we have to just connect them all like this. Okay, so that's how we need to connect this. So let's connect them together. So here is our NOT gate IC, and this is the first output, output one. Okay, so this should be connected to the input of the NOT gate. The first input is at pin number one, simply, right? Connect here. Okay, I have connected the output of the first NOT gate to the input of the AND gate. Okay, I have made this connection already. Now, the second, where was the second output? It's pin number 4. The NOT gate output at pin number 4 should be connected to the pin number 2 of the AND gate, because pin number 2 is the pin number 2 is the second input of the AND gate, actually, right? Now, let's connect the third output, which is here. So this should be connected to here is a caution. Pin number 3 is not the input of the AND gate, as you can see. That's why pin diagram is important. Yeah. So as you can see, this the pin number 3 is not connected to anything. So Yes, there are some cases, there are some pins which sometimes they are not connected to anything. So as you can see, the two inputs are 1, 2, and 4 and 5, not 3. Okay, so skip 3 of the AND gate. I mean AND gate IC. So the third output of the NOT gate should be connected to the pin number 4, not 3. Pin number 4. Okay, because that's how the IC is made. Okay, so let's go to the last output. Where is the last output? Here. So last output of the NOT gate should be connected to pin number 5. Pin number 5 is the last input of the AND gate. Okay, pin number 5. Okay, so all the inputs of the AND gate are connected. You can see. Okay, now we have the output pending here. The output of the AND gate is pin number 6. And as you should remember that if all the inputs of the AND gate are 1, then it should produce 1. Otherwise, it will produce 0. I mean, if there is only one, if at least one 0 comes in the input as of the AND gate, the output will be 0. So to produce output 1 from the AND gate, all inputs needs to be 1, right? Then it will produce 1, and we will feed this 1 to an LED. Okay. So so our pin, just remember here, and we have a very important thing left for the IC. What is that? We have not done something important of all the ICs. Power, exactly. I almost forgot and just remembered right now. So we have to connect the power pins of all the ICs. So we have 3 ICs. So to supply power, let's take another power supply, because these will be used as inputs and other works. So let's take another power supply. Do not mess with these power supplies. So let's take a separate power supply for that to power up the ICs. So here's the so let's take another power supply. Okay, so let me just connect the positive terminal to the breadboard, because I want to make a common positive terminal and the power supply source line here. So I have, this is my power supply which will supply the power to all ICs. So I have connected a node. As you should remember that this line is connected horizontally. So if I connect a 5 volt right here, I can take 5 volts from here, from any pins of this line, right? So this is right now. So this is my 5 volt line. Okay, this is my 5 volt, and let me connect the negative or ground here as well. So the above line is, suppose this is ground. So the bottom line, the bottommost line is our 5 volt. So let's connect them to the VCCs of the IC. So every IC is sorry. So this is the power pin. I mean, pin number 14 is the power pin of the IC. So you need to connect pin number 14 to the 5 volt line. So here is my 5 volt line. I'm connecting this here. And for the second IC as well, I'm connecting the pin number 14 or power pin to this line. I'm connecting the third IC's power pin to this power line. Okay, so now, and the IC has ground pin as well at pin number 7. We have to connect the ground pins as well. Okay. So we need to connect these ground pins as well. So as I have mentioned that this power supply's ground pin is right here. I have connected the black terminal or negative terminal right here in the second a second line actually. So I need to connect the ground pins of all the ICs to this line. Okay, so I have connected the first IC's ground pin, second IC's ground pin, and the third IC's ground pin. Okay, so the IC is now powered up. Okay, the ICs, all the ICs are now powered up using this power supply. Now, so all the ICs are powered up, and now we have the AND gate here. AND gate output is at here, is at pin number 6. Now we have to deliver this pin's output to an LED. So let's bring an LED from here. So there are two types of LED here in Tinkercad. So we will be using we need to use green LED, but to use green LED we can use this is the LED RGB. So this is an LED that can emit different colors of light. I mean RGB light. So there are many terminals for this LED, but we do not need to use every pins of this LED. Let me just describe how does this work. So if you take this LED RGB, then if you hover your mouse on the pins, as you can see, the first pin is red. So if you connect with this pin, the LED will emit red light. Okay. And if you connect on the second pin is cathode, this is the common, this should be grounded actually. So nothing important with this. I mean, it's important, but it's not related to color. Okay. So the third pin, if you hover on third pin, it's called blue. So if you connect this pin, it will emit blue light. And the last pin is green. So we need to use this. We want to use this green pin. So we just need to connect this green. Okay. So yeah, before connecting this green, okay, let's see. Uh, so we need to connect the output of the AND gate, which is pin number 6 here, to the green pin. Okay, and you need to connect the cathode as well, which is the second pin of the LED. It should be connected to the ground. Okay, so the ground pin, as I have mentioned, that the second line is ground. I am connecting here. Here we have ground. Okay, so the LED is connected, but yeah, there will be a problem. I will show you after simulating. Okay, so I think this connected, right? So here the output of the LED, so output of the AND gate is now connected to an LED, right? And LED is other terminal is grounded. So when there the AND gate produces one, then the LED should emit light, and if it produces zero, then the LED should not emit any light. Okay. There will be a small problem that's not fundamental, but let's see. Okay, so I think we have connected everything. Now we can start our simulation. Let's see if any problem arises. We will debug it. We will just debug it after simulation. So let's run it. Right, start simulation. Okay, now we have to correct the voltages. Right now, as you can see, that what is the situation? Uh, 5 volt, 5 volt, I see. Okay, let's start. Oh, yeah. Hex inverter and dual 4 input gate. Okay. I'm just checking all the voltages are correct or not. So we have to correct. I mean, okay. The switch is working or not? Okay. Hmm. Five, 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 five. Hmm. Are you getting any results? Are your lights turning on? Okay. In my case, I have done mistakes connecting the power pins of ICs, but okay, that's now corrected. Negative, positive, negative, positive. Okay. I should work. Mm, 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 Something. Oh, there should be something like Barclay or something. Yeah, I will fix this issue. But have you got something like this? Is your LED burst out or something? Yes, and that's good. And yeah, that should be okay. Okay. Zoom out. All So have you been able to burn the ICs? Yeah. Oh, well, yeah, so that's what I want. Yeah. So yeah. So the as you can see, in some cases the IC will burn, and in some cases the LED will burn. But why this is burning? If you hover the mouse on the burning, it will show you the reason. But yeah, let's check. So if you hover on the IC, it can show different things, but in my case it is showing that this device broke because of current through pin 1 I is in one so for your cases it may be different, but for different reasons the ICs can break actually. So to how to solve this? So actually, as you can see, the current or voltage is much higher than the planet that it can handle. So we have to limit current, right? So to limit current, we need to use a resistor, small resistor. So before connecting this to LED, let me just draw. So that's why in some cases simulation is important, because if you would do this in practically without simulation, the ICs will burn, and this, yeah, that would be. These ICs are very less expensive actually, but for other chips, very expensive chips, you cannot afford to run like this. So for that, we have to simulate that circuit and check the current levels and etc. and see if the IC will burn or not. That's why simulation is important actually before making the actual circuit. Okay, so okay. So I wanted to describe one thing, that how can this can be a possible fix. There are different fixes, but this can be a possible fix, that we have an AND gate and it is producing, suppose it is producing, sorry, 1 or 0. Okay. So when one, what does one mean? It is producing something like 5 volt, or it can be lower, but it's near 5 volt. So an LED cannot handle that actually. Okay. Suppose this is an LED, and suppose, and the resistance of this LED, suppose this is 5, suppose this is 1 kilo ohm. The resistance, suppose the resistance of this LED is 1 kilo ohm. This is not correct number actually, but let's assume the resistance of this LED is 1 kilo ohm. 1 kilo ohm means 1000 ohm actually. Let me just write it simply. 1000 ohm. And you have in the very first class you have learned about Ohm's law, right? Ohm's law tells you how much current it will flow through this LED. So according to Ohm's law, we know that I equal to V divided by R. Simply the current equal to voltage divided by the resistance. A simple Ohm's law. You can just remember this. This is simple Ohm's law. And suppose here the voltage is 5 volt. Okay, so 5 volt, and the resistance is let's make it 100 ohm. That way it will be easier to explain. Suppose the resistance is 100 ohm. So voltage is 5 volt, resistance is 100 ohm. Then the current would be 0.02, right? I mean, 5 divided by 100, it's something like 0.02, which is in terms of milliampere. So the LED cannot handle this amount of current actually. That's why actually it's burning. Okay. So why is it burning? Because the resistance amount is low, and that's why a high amount of current is flowing. To limit that current, we can use a resistor in series with the LED. So to avoid this issue, what should we do? We should just connect a resistor before the LED. Okay. So So this is the output of the AND gate. So before delivering this output to the LED, we will use a separate resistor before that. Then we will send it to the LED. Okay. So we have to connect. We have to. You can use a resistance of 120 ohm like this. So what we are doing by inserting this resistance, we are limiting the current. Because right now, without this resistance, right now the current level is so much high that it is burning the LED and the ICs actually. So if we include a resistance like this in series, I mean with this LED, then it may fix the issue actually. So let's do that. So let me take a resistance. So I'm taking a resistance which is currently 1 kilo ohm, but 1 kilo ohm will be too much. So let me just reduce it to 0.1 kilo, 0.12 kilo ohm. And we need to connect like this. The output of the AND gate should be connected to one of the terminal of the resistor, and the other terminal of the resistor should be connected to the LED. Right now, and no IC is burning, and the LED is also intact.